This problem describes a scenario where we have two posts, one that's 12 foot high and one that's 28. This is obviously not being drawn to scale because it's not more than twice as high. But anyway, we got these two posts and they're 30 foot apart, and we're going to put a stake somewhere between here and attach wires to that stake to the top of each post. So let's draw a wire from here to here. That's a pretty crooked wire, can't draw straight. And then a wire from here to there. And so we want to do this using the minimum amount of wire possible. So that's giving away that we're doing an optimization problem. So our first step, that's the easy step. What are you trying to maximize or minimize? Give it a name. In this case, I'm minimizing the amount of wire. I'll call it W. You can call it whatever you like. Second, you create some sort of equation for that thing you're trying to minimize. In this case, I've got these two lengths of wire, and I want it to be as small as possible. So W is equal to length 1 plus length 2, where one of these is length 1 and one's length 2. All right, so that at least gives me something to start working with. I need to get this down to a single variable, and there's several ways to solve this problem. I'll use the more algebraic way by saying, let's suppose we put that stake here at x. Then obviously this is 30 minus x from this other side. So that's the distance from this smaller stake is x, where this is 12 and this is 28. Well, now I can tell you what those lengths are by using the Pythagorean theorem. Now that gets a little messy fairly quickly because of the square roots, but this length is going to be equal to the square root of x squared plus 144, 12 squared. And the other one is going to be equal to the square root of 28 squared. And I'm just going to leave that as 28 squared. Let's put the x first. So I'm going to have 30 minus x squared plus 28 squared. And we'll just leave it until we need to actually calculate what 28 squared is, if we ever need to. That gives me the different lengths of wire, total length of wire that could be used in this scenario. We can see that that is going to be trapped from x equals 0, meaning you put the stake, you actually attach the top of this one to the bottom of that one, which I don't know if that's anything you'd want to do. And it could be as big as 30. So we've got this function on a closed interval. So we'll go through our process of finding the max and min. We know that it could be using, we could use 0 or 30. That's our endpoints. On this problem, we could use 30 or 0. And like I said, that's the endpoints. Or we can use critical points. So let's find the critical point, and then we'll plug these things in, figure out which gives me the max or the min. Well, we've got to find W prime, which is a bit messy because you need a chain rule. Here you need a chain rule, and then there's a chain rule inside the chain rule. I'm going to cheat and tell you, for a problem like this, on homework, you might want to cheat and use some sort of resource, but it turns out if you take your derivative and simplify it completely, you get something like this. X times the square root of 30 minus x squared plus 28 squared plus, so I'm combining these two, there would be two radicals here that I have to combine, and this would be what you'd end up with, x minus 30 times the square root of x squared plus 144. So it's not too hard to imagine where that's coming from. And then the denominator is just the combination of both of those, square root x squared plus 144 times the square root of 30 minus x squared plus 28 squared. There's your second derivative. Your first derivative. And I need to set that equal to 0. I need to know where it doesn't exist. Well, these exist. This is always positive underneath that radical. This is always positive. You'll never get 0 in the denominator, regardless of these x's that you choose. So you're good there. So it's going to come from where the numerator is 0, which is going to give me x times the square root x minus 30 squared plus 28 squared equal, when I set it equal to 0, I'm going to get a minus on this side, x minus 30 times the square root x squared plus 144. And to solve for x, I'm going to square both sides. That's going to give me x squared times x minus 30 squared plus 28 squared. It gets rid of the square root on that factor. And the same way over here, it's going to give me x minus 30 squared and gets rid of the square root on this factor. And now if I clear out these parentheses on this side and on this side, what I'm going to have is x squared times x minus 30 squared plus x squared times 28 squared equals, over here, it's going to be x squared times x minus 30 squared plus 144 times x minus 30 squared. Sorry, I didn't leave enough room there, but that's right there. And the nice thing is that this simplifies a lot just by doing that. And so I end up with x squared times 28 squared equals 144, which is 12 squared, times x minus 30 squared. So since those are all perfect squares, I can take the square root of both sides and get x times 28 is plus or minus 12 times x minus 30. And solving this, I get that x is equal to 12 times x minus 30 over 28, or x is equal to negative 12 times x minus 30 over 28. And if you work these two out, let's see, this one with the plus is going to end up giving me x equal negative 360. Probably should have just cleared parentheses and that, but anyway, you do get x equal minus 360 on this one. And this one ends up giving me x equal 9. So this one doesn't make any sense. So I only get the one critical point, and that is 9. All right, so now I want to check where my absolute minimum occurs. So I want to minimize the length of the wire. So let's see, plugging in 0. I'm going to go back in here and plug in 0. I'm going to end up with square root of 144 plus, on this one when I plug in 0, I'm going to have the square root of 30 squared and 28 squared. If you work this out, this ends up being 12 plus 41, so somewhere around 53. So rough estimate. If I plug in 30, I end up with 30 squared plus 12 squared from the first one. Sorry, I'm kind of cramming it in here. And then from the second one, I plug in 30, that's 0, and I get a 28 squared, so that's going to be 28 from that. And if you take a calculator out and approximate that, that ends up being about 60.3, so bigger than the other one. And then finally, when you plug in the 9, what you end up with is the first radical here would be 81 plus 144. That ends up being 15 when you take the square root. This one, when you plug it in and take the square root, you'll end up with 35, so this is 50. And so this is the one that minimizes. And so the last step is to answer the question, where should the stake be placed to use the least amount of wire? This says I should place it 9 feet from the base of the 12-foot stake, and therefore it would be 21 feet from the base of the other stake. So this one, a little messy in terms of the algebra and the arithmetic, but the process is what's important, how you find that absolute minimum in this case.